All right, everyone. So we're going to be continuing with our algorithmic accountability work today. The main thing we're building up to today is quantitative definitions of fairness, which are central to almost all of the algorithmic accountability work that's been done so far. Certainly everything we saw last week. Of course, race and gender bias are extremely popular algorithmic accountability stories, and we'll be looking a lot at that. But you can also imagine different groups like rich and poor people. We'll also talk about more general considerations of data quality, feedback loops from using algorithms, how people interpret the results of algorithms. We've been spending a lot of time on the sort of core algorithms themselves. That's by design because there aren't many places where you can get that type of discussion. We're gonna sort of bring all of the other issues in scope, and you will find many other discussions of some of these broader issues. So we're going to start talking about trying to measure fairness in various ways. There's some really challenging problems when you work with observational data, going back to some issues around causality. We're going to go back to machine bias and talk about the fairness criterion that ProPublica used. The core of this class, I think, is the impossibility theorems, which put limits on what types of fairness you can have. And we're going to see actually over 20 definitions of fairness and show how they relate. And then we're going to talk about all of the stuff around it, including some very interesting case studies, such as the child abuse screening hotline that we looked at earlier. So let's start with analyzing experimental data. You've probably seen a lot of this sort of thing. These are an analysis of hiring decisions in the sciences. This is a huge paper on this whole question of what does the career path look like for women in science, and what are the disparities. So what do you see here? What are we looking at? Yeah, it's this sort of multi-stage process, which is very common. Almost every case we will look at is this multi-stage process, including criminal justice especially. What are the numbers suggesting?
Well, at each, I don't know, it's hard for me to, I'm like more of a visual person, so this is like tricky to read for me, but at each juncture, the percentage is increasing, so at each stage that the women go through, like they're somehow able to perform better or get better outcomes.
Right. And equivalently, you know, if you look at different data sets, you'll see the reverse, right? You'll see the how to put it, the traditionally disadvantaged group looking worse at each stage instead of better, for example, right? So it could be one way or the other. What can we conclude from this type of data? What can we say about these processes? Can we say anything about bias for or against the group in question just from these types of statistics?
Isn't this incomplete?
Incomplete how?
I mean, we spoke about how confusion matrices would be one way to defend or accuse someone of bias. I don't think you can make a complete confusion matrix out of this data.
So we're getting immediately into a very fundamental problem in all of this work, which is, and I'm going to draw a very abstract model that applies in a lot of different fields. So the basic idea is that we have some process which is supposed to output a yes or no decision, or let's say let some number of people through. And we have some pool of applicants which, in the simplest possible case, we're going to say break down into, well, let's call it qualified and unqualified in this case. This could also be, are going to end up committing a crime while on bail or not. It could be, are going to pay back the loan or not. It's often some sort of predictive variable. It's often some sort of ranking or measure of merit in some way. But really what it is this sort of question of should they be let through this filter, right? So there's a certain number of people. It's not always people. Could be, applications for a particular project, right? Grant proposals or something, right? And as much as possible, we would like this to only let the good ones through, whatever good ones means. And then we've got different groups, right? So the situation is that's group B, that's group A, and we've got some qualified and unqualified people. Again, I'm using the words qualified and unqualified in very generic ways, right? In group A and B. And the idea is at the output, we have a certain number of people from group A and a certain number of people from group B, and we would like to let mostly the qualified ones through, right? So this is make some sort of decision. And this setup shows you immediately a few different things. One is that just looking at the ratio of people to group A to group B doesn't really tell you what's going on in this box. We normally are interested in bias inside this box, but we can't from just these outputs and these inputs, right? So the inputs that we have on this slide are, we have, the number of people in group A, we have the number of people in group B, and then we have these numbers here as well, right? We just have the counts. And from those four numbers, we can't really determine what's happening inside this box and whether it is biased. Where here we're going to define bias is as, we are preferring qualified people of one group over the other. And the reason we can't is because we don't know what the input looks like. We don't know what the fraction of qualified people in the different groups are. So we can't, and this should be, if you stare at this chart for a second and you think about it, this should be clear, right? We can't disentangle the fraction of male and female applicants from the quality of the applicants, right? Maybe all of the women come from better schools, or had more NSF grant funding in their prior careers, and that's why more of them get hired, or maybe not, right? So that's the basic setup for almost everything that we're going to do in this class. And this is part of why answering these questions is very hard, is because we need to know or control for the characteristics of the applicants. Now that in itself is a particular idea of fairness. That is a quality of opportunity. You can also defend a different principle of fairness that says, you know what? We got to normalize these counts. I don't care what the applicants are. I want equality of outcome, not equality of opportunity. And that sort of is not identical with, but sort of heads towards the affirmative action model. So real considerations of fairness are much more complicated. But this is the idea and the setup for this. There are a bunch of reasons that, a bunch of complications in just measuring stuff here. This is a very famous paper and actually lawsuit. What happened here was the University of California at Berkeley was sued in the early 1970s on the basis that their admission rate for female students was a lot lower than for male students. And shortly thereafter, this paper was published. And this is an instance of something known as Simpson's paradox. What had happened was that if you analyze the overall numbers for the school, the admission rate for women was lower. If you analyzed the admission rate by department, almost every department had a higher admission rate for women. So how can that be? How can you have the overall admission rate for the entire school be lower than men, whereas for each department it's higher for women? Yeah.
The departments that they have could be harder for women to get into in general?
Warm, getting closer. It requires one other factor. So take a look at this diagram for a second. This is how many women apply. So each of these is a department. This is how many women apply to each department. This is how many are admitted. This is, oops. And then the size of the box is the size of the department. And they're showing a trend line here. Trend line is saying that the higher the percentage of women applicants, where there are more women applicants, there are fewer of them admitted, right? So basically the women are applying to departments where there's a lower admission rate, generally. Now, there may still be a problem here, because what this turns out to be is, the women apply to the humanities where they have a huge number of admissions, and so they can only take 10%, and more men apply to the sciences where basically they take everyone who applies because only people who are qualified apply. So there's still complexities at play here that we might want to take care of. But I am suggesting that how you group people changes the numbers, and you can actually have overall different balances in the aggregate versus the individual units. So I'm gradually building up some of the complexities of asking this question. That's my goal here. Simpson's paradox appears in a bunch of other places too. So another form that Simpson's paradox takes is when you do a regression model with only one variable, you see a positive trend. When you add another variable, you control for another variable, you see a negative trend. So an example of that would be, let's take our Nike shoes example that we studied when we looked at regression. Let's say you look overall and you say, oh, the people who wear these shoes are, if I just look at this one variable, did you wear a shoe, I see a positive trend for improved performance in the race. But when I add in this other variable of were you running at morning or night, because generally people have slightly better performance at night, you actually see a negative trend for those shoes, potentially. So as you add variables to your model, in this case adding the variable of what department they applied to, you can actually reverse the regression coefficients. And there's a famous example in healthcare where it looked like a drug was better for everyone together, but was worse when analyzed at two different hospitals. And the answer to that puzzle is, well, the patients were different at the two different hospitals. Okay. This gets us right back to the question of controlling for other variables. This was an analysis. I don't remember if we've looked at this one. This was a nice analysis by the Miami Herald Tribune looking at sentencing lengths, again, for black and white defendants. And you can't just ask, do white defendants get longer or shorter sentences than black defendants? Because, again, it's the input population problem, right? Are they committing the same types of crimes? And so to do that, they used this point scale, which was developed about 10 years prior, to try to even out sentencing. So you get assigned points for previous criminal history, basically. And the reporters can put sort of people into buckets by how many points they had, and then compare people only within the same bucket. So that's an attempt to control for the differing characteristics. So right away, if you're going to do these types of analyses and look for bias inside this decision box, you really need to control for the characteristics of each group. So we talked about qualified or goodness or something, right? It's the characteristic on which the decision should be based. So if you believe that the sentence length should be based in part on your previous criminal history, then that needs to be compared when you're comparing sentence length. Really what you'd like to do is an experiment. What's the difference between experimental and observational data? Yeah, you control a variable when you're doing experiments. So we talked a bit in our discussion of causal modeling of the do operator. An experiment is where you get to force the value of a certain variable. So this is an example where they took pitch decks and they changed the names and photographs of the people who were supposedly the team behind that pitch, and they sent them in a pitch competition to a bunch of VCs. And what do we get here? You want to be an attractive man. That gives you the highest likelihood of winning the pitch competition.
But less attractive women are less likely to, wow.
What does this mean?
In,
Yeah, what does NS mean?
Not.
Not significant, okay. So what they're saying is it's within statistical noise. Yeah, according to the P equals 0.5 definition, which we're going to take apart next class.
And how did they judge attractiveness?
Good question. I don't actually know because it's been a while since I read this paper, but I can think of a few ways that it's been done. So how would you judge attractiveness for this experiment?
Find some research that has already done it.
Okay, but how has it been done?
And use their data set, use their formulas.
Symmetrical faces.
Symmetrical faces, or high facial contrast.
Zuckerberg approach. Make people rate them.
Yeah, much simpler approach is just to ask people to rate them.
Tippable.
Yeah.
Yeah.
Which of course will depend on who your raters are, but anyway, you can make this work. So this is as clear as evidence of bias ever gets. When you have an experimental manipulation of the variable that you think people are biased on, you can pretty much just nail it down and prove it, right? Like this is, yeah, there's gender bias in pitch competitions, right? As opposed to this case where it's hard to say what's going on. Maybe the women are just better scientists, right? Or vice versa, depending on the data you're looking at. Sometimes you get what's called a natural experiment, which is where there's randomization or other control introduced. Can happen in a lot of different ways. Laws changing in some states but not others is a classic natural experiment. A natural disaster can be a natural experiment because it forces everybody to rebuild at the same time. There's various ways this can happen. This is a nice piece by a Swiss paper looking at deportation hearing cases assigned to judges. The judges are appointed by different parties, some of which are more favorable to immigration than others. And what they found is that, yes, certain parties have significantly higher rates of, I forget whether this is denying or allowing the appeal. Deportation rates, so this is denying the appeal.
That's Barnaby Skinner is a lead student from 2016.
Yeah, that's right.
I was
That's
TA,
right. Yeah.
Or 2017.
Yeah. So this is an experiment because of the randomization across judges. And randomization breaks the correlation between the judge and the case. So summed over many cases, you can get these types of results. And so this is another experimental result, which is pretty good, right? Maybe not quite as good as doing your own manipulation, but pretty good. Slides out of order. This is a description of the bias on the bench. So this stuff, this is what's going on. Their methodology post, which of course you all should be reading the methodology posts on data stories and writing them. And what I want to draw your attention to is this: grouping defendants who committed the same crimes according to the points they scored at sentencing. So they used histograms 1 point wide, basically. And then they evaluated the differences within each bucket. So we've talked about adding a variable to a regression model to control for it. You don't even need to get that complicated. Just binning people and comparing them by bin does basically the same thing, right? So very simple models can be used to control for these factors. And then they computed a weighted average of the difference in sentencing time across the buckets. Weighted by what, by the way? When they say weighted average, what do they mean?
The number of defendants?
Yeah, exactly.
Okay, just
Right. So if you have 1,000 people in one group and 2 people in another group, you don't want to weight them evenly. This is a New York Times story about racial bias in New York State prisons, which this is common and complex. Here they're looking at disciplinary rates. So how often someone gets disciplined in various ways. And what they're arguing is that the disciplinary rates are higher than the population rates for black defendants, and of course, accordingly lower for white defendants. Thinking about this model again, what's the issue with interpreting this data? So does this show that the prison staff are harder on the black population?
It could also mean that they just behave differently in prison.
Right. So you've got the same problem, right? You don't know about the population, right? We can certainly say that this data is consistent with bias on the part of the prison staff, but we're going to need more to nail this down. So they do have more. We don't have a controlled experiment here. We don't really have data on what the prisoners are doing.
You can look at, there is a lot of data about disciplinary action for early childhood and public schools.
Mm-hmm.
So actually the disciplinary rates for inmate populations and for pre-K
Mm-hmm.
match up nearly exactly.
Interesting.
So that's like when you're looking at this maybe being an indicator that their behavior is different and warrants some sort of disproportionate response, it's hard to make that argument for pre-K when someone has not had as much time to develop.
Interesting. That's a kind of indirect evidence. Yeah, I like it. This is what the Times did. So here they are talking about this problem of differing populations. Greater share of black inmates are imprisoned for violent offenses, and minority inmates are disproportionately younger. Right, so they're addressing this issue in population difference. They know it, and we're going to see this in the ProPublica data as well. It's the same issue: more criminal history, younger. This sentence I'm disappointed with, even after accounting for these elements. They don't say how they accounted for them.
Yeah.
Right, so I don't know if it's a statistical method or if they're just like, they just don't believe it. Like, I find that very unsatisfying, and I hope you will all do better. But this is interesting. The disparities were often greatest for infractions that gave discretion to officers, like disobeying an order, right? So where there is more choice in the disciplinary action, then we see greater disparity. So here's what that looks like, right? More disparity for more discretionary offenses. So this is how they attempted to compensate for this problem of differing populations. And it's a challenge, right? Because, you know, the rest of the article is a list of horrifying incidents of racism inside the prison system. So call that the qualitative data. And you don't want to discount the qualitative data. The qualitative data gives you a detailed picture of what is happening at ground level, right? That's the only way you can get that information, is you need to understand these individual stories. Otherwise, you don't understand the mechanics of what's happening. Also, it's important for storytelling, right? You got to give examples. If you just give statistics, it's not going to have the same effect on the audience. They're not going to remember it. They're not going to understand it. But this is how they're trying to make this case in a statistical sense. So this is the more common case. The natural experiment case, the natural control variable case are rare. So more often you're going to be dealing with tricky methods to try to understand what's happening. And of course, you always have to consider the possibility that there isn't bias, because otherwise, why are you even looking at the numbers if you already know the answer? This is a similar one. Again, this is a New York Times piece. This is use of lethal force. Again, we've got a control here. Look at this phrasing, in similar situations.
Where is this from?
This is another New York Times piece, which is...
The graphics look very un-New York Times for some reason.
Oh, yeah?
Yeah.
Well,
like,
yeah, depth shot. It's an Amanda Cox piece.
yeah.
And this person who I don't know. But they went through and coded for what the situation was, right? So here's what they did. And when they say similar situation, they have some sort of coding system for reading these reports and then sorting them into categories, right? And so the categories they sorted into them are, you know, did they fire a weapon, and, you know, were they handcuffed, and blah, blah, blah. We could take this apart and look at how they tried to compensate. But you're always going to need something, right? Because normally when you look at these statistics, all you have are the raw rates, and you don't have the population characteristics. So that's the major challenge. So switching tracks, I'm sort of trying to give a bunch of pieces, and then we're going to assemble this. Why is there interest in using algorithmic decisions at all for criminal justice, hiring, child abuse hotline screening, lending, all of the stuff we've seen? Why are we doing this? Increase efficiency. Okay, so if you got to screen a lot of resumes, maybe you can make a computer do it. That's what Amazon was trying to do, for example.
So have a standard, like consistent standard, so it's now like human judgment.
So right, so to standardize or the process, have make sure everyone is given the same sort of treatment, at least the same sort of treatment in as far as they have the same data on them, which is not assured. Why else?
I think to increase, I don't know, it's sort of counterintuitive, but to increase transparency for decisions.
Mm-hmm.
Because if a human is making a decision based on their own personal judgment, it's often not quantifiable what went into that decision.
Yeah, so this is an interesting argument. I've found that some people feel that algorithmic decisions are a black box. They're complicated. Some machine learning models are not explainable. I mean, how do you explain why a convolutional neural net made a choice, right? I mean, oof.
But how do you explain why a caseworker makes you can't do the same thing for a caseworker, so.
Right, some people feel that human decisions are a black box, although you can ask a human why they made a choice. Although the answer they give you may not be the reason why they actually made the choice. So it's not a simple comparison. And I think people tend to have a human or algorithmic bias and tend to imagine that one of these is more explainable than another. Why else are we using algorithms?
For social services, because budgets are constrained, austerity, so it's a way to augment the human capacity you are able to have.
So that's an efficiency argument again. What I'm driving towards is prediction, right? So in general, across a wide range of fields, simple statistical methods, and I'm not talking neural nets, I'm talking regression with 2 or 3 variables, tend to be better predictors. So let's see what that looks like. This is a paper about using algorithms for risk scoring. So this is the machine bias case. And there's been a bunch of work like this, but this is a significant one, which is they use actual data on judge decisions from, I think this is in New York State that they use. I don't think it says here. I think they do New York and a national one. And they show that basically judges are not super great at predicting who's going to be rearrested after being released. And just based on, never mind the 137 questionnaire that Compass has, just based on data available at the time, sort of case history stuff, case history and demographic stuff, you can improve prediction so much that you can put a lot fewer people in jail or reduce crimes by keeping the right people in jail, and do that while reducing racial disparities. Now, what exactly they mean by reducing racial disparities, we have to look at it, the paper, and take that apart. But basically, human judges are not great at deciding who is a safety risk. And, I would argue that this is not surprising. And the reason I think it's not surprising that human judges aren't very good at this is because they don't generally track their decisions and the outcomes, right? It's hard to get good at prediction if you're not tracking your predictions and the true outcomes. And almost nobody does this. I'm sure there are a few judges that do it, but it's not a standard thing. Right, so possibly if all judges tracked their predictions over time, then they could close this predictive gap. But at the moment, we know that basically linear regression is going to do so much better that there is a huge potential public benefit. And this is why people are pushing for this. In general, I said simple statistical models are better at prediction. This doesn't mean that statistical models are good. Often it just means that the problem is very hard, right? So your model may only get 30% accuracy, which is not great accuracy, but if the humans are only getting 25, it looks better. I'm going to put a lot of caveats on this. Accuracy is not the only measurement that you could be interested in. This doesn't account for fairness metrics. Even if the humans and the statistical method have the same accuracy score, the errors could be distributed differently. There's all kinds of potential problems with this. But here's the beginning of a table from this paper. And what I want you to see here is that this is a lot of different fields, right? This holds among a lot of different things. So this is education. This is medical. This is criminal justice. There's some more medical there. And so across many, many different domains, generally simple statistical models, what used to be called actuarial models, perform better. And so there's, I would argue that your sort of baseline suspicion is that the statistical model is going to give better predictions. Okay. So better predictions have consequences. If you know that someone's not going to commit a crime, you can release them from jail. If you know that someone is going to succeed in this job, you can hire them. So accuracy is important, but it's not the only criterion. And I think this was really we're critiquing this machine bias piece very heavily in this class. But it was still an extremely important piece of journalism because it opened up this whole conversation and spurred the research that we are talking about today. And just to sort of revisit this is what we saw. So this is the actual raw data. So this is my friend Stephanie, who has been working on this stuff, made this chart when she was trying to understand it. And you can see that there's 8 numbers here, and you actually can't do this comparison without 8 numbers. What you really have is 2 confusion matrices, and you need a confusion matrix to generate the false positive rate, and you're comparing false positive rates for 2 different groups. So you actually need all 8 numbers to get this. This is kind of the equivalent of dimensional analysis. Has everybody run into dimensional analysis? This is where this is used mostly in physics, where you sort of work out what the formula has to be based on the units. So if you know you're going to end up with a speed and you have a distance and a time, well, you have to divide the distance by the time because, miles per hour, right? So this is sort of the equivalent I showed you the risk ratio where, like, okay, you're not going to need 4 numbers to compare differential risk. You know you're going to need 8 numbers to compare differential accuracy metrics. So this is what we had. Note that the base rate of rearrest for black defendants is much higher. And we saw that in our tests as well, right? So basically, the left side of the chart tends to be higher than the right side of the chart. They are rearrested more often. Now, that could be differing. What the behavior could be different. It could also be biased in the arrest data, which we're going to talk about. But differing base rates turn out to be a major problem. So this is sort of how there's sort of this fight, and you can read several rounds of back and forth between ProPublica and Northpoint, who created the COMPAS scoring system. And there's like 100 pages of this stuff. But if you really boil it down, this is what the argument is. ProPublica is saying, hey, your false positive rate is much higher for black defendants than white defendants, which I'm producing here by labeling these numbers. Right? They're just calculations off the confusion matrix. And Northpoint's saying, yeah, but the positive predicted value is almost the same. In fact, it even slightly favors black defendants because they are slightly more likely to be rearrested at the same level of risk value. And one way to think about this is your reversing the conditional probability, right? Oops. So the false positive rate is, of the people who are not rearrested, how many were labeled high risk? The positive predicted value is, of the people who are labeled high risk, how many were rearrested? So you should all know from basic probability theory that reversing the conditional probability changes the number. And one way to see that, or to talk about that, is to use that diagram we had a couple classes ago, the quadrant diagram. You remember this quadrant diagram? So here it is. So we're going to say rearrest, not rearrested. And then the way this is set up is high risk, low risk. And then we've got some dots. For simplicity, we're just going to look at one type of dot. We have some people in each of these. And in practice, most people are not rearrested. And what we would like is that the high-risk people, basically we want this is a confusion matrix, basically. Basically we want the diagonals to have most of the dots, because we either want them to be labeled low risk and not rearrested, or high risk and rearrested. And so the more we have most of the dots in the diagonals, the better the classifier is. Now, if we're going to do that false positive rate, so FPR equals, let's label these cells A, B, C, D. I don't know if this is the same notation I used in the slide, so I apologize for that. So false positive rate is high risk given they were not rearrested. So if you're not rearrested, that's here. So that's the denominator, and the numerator is there. So B over B plus D. Okay? Here's where I really wish I had one more color. I guess I'll use the green. But the positive predictive value is rearrested given that you are high risk. So the given that you are high risk means this is the denominator, and that's the numerator. So A over A plus B. Okay? So the denominator is different. You're actually measuring as a fraction of a different population of people. The fraction you're measuring is on the right side of that bar in the conditional probability. Conveniently, it sort of looks like a denominator. And so the North Point argument is that you should be using all of the people who are labeled high risk as the denominator. And this actually corresponds to some pretty standard definitions from the psychological testing literature. The psychological testing literature, of course, they're concerned about fairness across race as well for, IQ and anxiety and school scores. And, they've been thinking about this for the last 100 years. And they normally use this, a definition that is more or less equivalent to North Point. Okay. I've been really tearing through this. I'm just trying to get us sort of up to speed. Questions or comments on this so far? All right, moving on then. So the positive predictive value is basically, you can think of it as what's the probability you're going to be rearrested for any given score, right? So this is a binary version of the problem where you're just labeled high or low risk above some threshold. This is the continuous version of the problem where we have a continuous score and it corresponds to some probability of recidivism, which means being rearrested. And as we saw earlier, this is more or less linear, which means that this score can be transformed into a probability. It's basically a probability, and that is a property known as calibration of a predictor. It's a very important property, and it's more or less the same between black and white. And it actually favors black at the high end here, slightly. So this is the continuous version of saying that you have equal positive prediction values. And here is the, and here is more for Publico's analysis. These are the curves for low, medium, and high risk. How many people were rearrested. So this curve goes down when someone is rearrested. This is a survival curve. And you can see there's clear separation between the categories. So the people labeled as higher risk really are higher risk, right? They're these red ones. And they're about the same between black and white. And if anything, the black survival curves are lower, which means that the predictor is a little more optimistic. So it's going to let more people go free. So this chart and this chart are basically the same information. This just introduces the time element. Now, here's the challenge. If you take your basic confusion matrix formulas and do a little rearranging, you can get this formula, which expresses the false positive rate in terms of the positive predictive value, and P, which is the base rate. So P in our case is how many people are actually rearrested. And here's the issue. If you set the false positive rates to be equal, and P isn't equal, right? So the base rate of rearrest is different, then the positive predictive value cannot be equal, or vice versa. So this is our first impossibility theorem. Again, you can get this just by starting with the formulas on Wikipedia and trying to derive FPR in terms of these things. So there's no magic here. And it says that you can't have both types of fairness at the same time, right? You can't have both the score means the same thing for black and white defendants, which is calibration or equal PPV, and we have the same false positive rate for black and white defendants at the same time. So you have to pick one or find some balance between them. And your homework for today is going to be playing around with a classifier to try to balance them. Turns out you can get almost as good as the compass predictor by just using age and criminal history. You can get nearly the same performance, which is interesting in itself. It says that this 137 factor thing is actually unnecessary, and that most of the information is contained in a small number of variables, which has explanatory consequences as well. All right, so then the question becomes, do we want to keep people in jail just based on their age? Because that's kind of what we're doing if we use these predictors. So that's our first impossibility result. And this is how they put it in that paper. I like this phrase, difficult stakeholder choices. And this, the goal of complete race or gender neutrality is unachievable, at least if you define it in terms of those two definitions of fairness. As it turns out, there are many, many definitions of fairness. And one of the things that has become a little clearer in the last 2 years of research is that they basically boil down to a small number, all of which are mutually exclusive. So let's set this up. Here's the notation we're going to use for the rest of this. So the idea is we're assigning a score to each person, which has some attributes X, and they're in some class A. So you can think of A as, race or gender or whatever it is. And we give everybody a score between 0 and 1, which, if it is a calibrated predictor, is going to be, think of it as a probability, more or less. And then we make this decider, this yes or no, by thresholding. And what we're trying to match is y. So if we had a perfect predictor, then we get c equals y. Okay, so that's the setup. Sometimes this is also called D for decision. Now there is a wonderful list that has been compiled. These are all of the definitions, quantitative definitions of fairness that have been proposed in the literature. So there's a couple dozen of these. And they operate in different ways. And if you go through this and you stare at it long enough, you can actually translate each of these into words. So for example, in any situation, right? So let's take the hiring example. Statistical parity, the probability of decision equals 1 given A equals A is same as probability given A equals something else. So that says that we hire the same number of men and women. Right? So that's a definition of fairness that's based on equality of outcomes. Whereas, let's see, equal positive predictive values says that given that someone is in a particular class and we decided yes, the probability that they actually were a yes, because we're talking about predictors here, is the same between classes. So this is, if we said that you were high risk, the probability that you were actually rearrested is equal between classes. So this is the calibration definition. And so on. Here's the one that ProPublica was saying based on true positive rates. You can also say, for example, let's make the area under curve the same. So AUC is this metric for classifiers that we looked at last time. You can say, let's make that the same. That's sometimes called accuracy equity. Calibration is the continuous version of equal PPV. And then you get into causality definitions. And causality, as we've discussed, is not something that is available purely from the statistics. You have to use a do operator. You have to imagine that you can actually change a variable. And so counterfactual fairness says that the decision I would have been hired or not hired regardless of whether I was black or white. That's what this says. The decision for one group is equal to the decision for a different group for that person. So if you stare at this long enough, you can actually translate each of these into words. And these are all definitions of fairness that people have proposed at various points. So now our task is to untangle these a little bit and talk about, and by the way, I highly recommend this reference. It's linked from the syllabus. It has this stuff in a lot of discussion and interesting references, including a recap of the ProPublica North Point argument. But we would like to simplify this a little bit, because this is really complicated. Okay. Questions before we go on? Pause here for...
There's a definition of calibration
Uh-huh.
in the AFST, the reading stuff, but I don't understand it.
You don't understand it?
Because it's slightly different from the definitions of calibration.
Uh-huh.
Here.
So let me load up that paper.
I don't understand why it's comparing each group, because J is
Uh-huh. So what it's saying here is that,
else.
so look at the structure of this.
Yeah.
It's saying that the probability of y equals 1 if we know they're in the group and they have a particular score, is equal to the probability that y equals 1 if we only know the score. In other words, what it's saying is that the probability that y equals 1 for that score, where in this case y equals 1 means the child will be placed in a foster home, is the same whether or not you take the group into account. Yeah, so what they're saying is, so take a look at this again. What that's saying is, if we take the overall, so for each score, so it's conditioned on S, so we're conditioning on this number, which means we're setting that number as the denominator, right? So we pick one of these, and we say the overall level at which y equals 1, which is the vertical axis here, is the same as the individual levels, which means that these two bars have to be the same height. So that's what they're saying. Okay. Yeah.
General question among all those fairness measures, is there anything that's most widely used, or a few of them that are recommended by, I don't know, groups that decide on these things?
So there are some that are widely used. So calibration is historically what the psychological testing world, which might be closest to what we're doing, has used for fairness criterion. But you can make arguments for other ones, and so we'll get to there in a minute. So these are all the definitions. Moritz Hart has proposed that we talk about mostly 3 conditions. And if you stare at that list of definitions long enough, you can probably convince yourself that almost all of them boil down to these 3 definitions. There's some that aren't quite there because the causality definitions involve counterfactuals, which aren't captured in statements about statistical independence, or not fully captured. But most of them boil down to these 3 things. The slides will be posted, by the way. So you can either say that, so let me try to translate these in English. C independent of A, so the choice doesn't matter what group you're in. So we hire the same number of men and women. C is independent of A, conditional on Y. So if we know what the true outcome is, so we know that you're going to be rearrested with a 50% probability, and it doesn't matter what race you are. Or separation, so this is the ProPublica version. So we, whether or not you're going to be rearrested doesn't depend on race if we know whether you've been classified as risky or not. So pretty much all these definitions boil down to one of these 3. And we're going to look at these in a little more detail. And what I've done is I've tried to tie them into legal and moral principles. Because I think actually all of these definitions are defensible in different ways. And in many ways, they recapitulate the arguments that we are having about affirmative action right now. This is part of why this is a hard conversation. And oh yeah, you can prove that you can only have one at a time. Although you can approximate multiple ones at a time, and that may be a good answer. So this demographic parity idea, this is equality of outcome. There's different ways of phrasing this. So the most concise way is to say that the classification is independent of A. And so, for example, you could make a classifier that chooses the 10 best scoring men and women in each group. Each of these definitions has drawbacks. There's usually a way to cheat. And the way to cheat is extremely important if you're talking about training machine learning algorithms, because they will cheat if they can. If you make a neural network to evaluate resumes and you insist that there are the same number of men and women hired, but you don't have the same number of qualified men and women, then what's going to happen is for the gender that has fewer qualified applicants, this just allows the classifier to pick randomly. It puts no constraint on, I've said choose the 10 best, but if all you say is that, then the neural network might just get lazy and pick random ones. All it knows is that you want the same number, right? So thinking about what it does not constrain is as important as thinking about what it does constrain. Also, the perfect predictor, which always guesses C equals Y, so remember, that's the perfect predictor, is not allowed under this definition if the base rates differ. Right? So if you had perfect prediction of who's going to be rearrested, but you knew that black defendants are going to be rearrested twice as often, then the perfect predictor would violate demographic parity because you don't label the same number of people as high risk. Nevertheless, there are legal and moral principles that embody this idea. Calibration. Yeah, this is a classic definition. This is the one which was, I think everybody building these things thought that this was the one you wanted until this exploded into public view with the ProPublica story. It's still a very important definition for a variety of reasons. The reason it's called sufficiency is, what it's saying is that if you know the score, right, how they're ranked, right, the risk score that they got, the outcome is independent of the group. So in other words, the risk score is sufficient to guess at the outcome. So this symbol is statistical independence. So what this means in terms of actual numbers is this, right? This is the positive predictive value. The probability that the true outcome is 1, given that we said that it was going to be 1, is the same between each group. And most machine learning algorithms are designed to do this. The accuracy, most machine learning algorithms are scored on like F-score or accuracy or something. And most of those metrics that we use in training algorithms or optimizing the algorithms will produce this condition. So it's natural in a certain sense. However, you have at least 2 problems. One is that you may not want to treat everybody fairly. Remember, under US law around protected classes doesn't say treat everybody the same. In particular, think about the Americans with Disabilities Act. If you can't discriminate against someone with a disability and you have to build that ramp, that's not treating everybody the same. That's because we are concerned with equality of outcome in such cases. So it's entirely defensible to say that this is not the definition that you want in certain cases. And then you can also get different accuracy. This is why this has been called sufficiency. Here's the idea in terms of a causal diagram. You're saying the outcome is correlated with the score, but there's no direct correlation between which group you're in except through the score. In other words, another way to think about this diagram is all of the information about what group they're in is contained in the score. Right? So if we know R, we know everything that matters about A. That's why this is called sufficiency or separation. And then the last one, or sorry, that's why it's called sufficiency. The last one is separation or equal error rates. And here the idea is we want to normalize the accuracy between groups. I use accuracy very loosely. Accuracy as a technical term for confusion matrices, but could mean false positive rates, could mean AUC, could mean a lot of things, right? But if we have this condition, then we get all of those. So this implies, for example, equal false positive rate, true positive rate, accuracy, and AUC. All of those things are implied by this, Right? This is why these definitions are useful, is they fold in many, many possibilities. And again, this is the flipping of the condition, of the conditional probability. It's what we had here, just reversed. Right? It's different denominators. The simplest way to build a classifier that does this is to use a different threshold for each group. And that's what you're actually going to do on the homework. And there's actually some theoretical work showing that taking a classifier which is calibrated and setting different thresholds on each group produces a classifier which is, obviously satisfies this condition, but is still mostly calibrated. It will, if the original predictor was calibrated, then the modified predictor will be close to calibrated. Of course, you can make that more formal. And this is what you're going to do in your homework. You're going to take a calibrated predictor for the ProPublica data, and you're going to modify it by using different thresholds for black and white defendants. And you're going to tell me what happens to the calibration and the accuracy. A potential legal roadblock to using this is that if you use different thresholds, and in fact most of the methods which achieve this have to use group membership explicitly. So you end up explicitly building your algorithm to depend on, say, race. That may or may not be legal in various cases. We're seeing a court case right now, the Yale and Harvard cases, where the plaintiffs are Asian students who feel that they're being discriminated against by the policies that encourage Black and Latino students. But in other cases, there's no case law saying that it's legal. However, again, you can argue that it's an equality of opportunity thing, right? Everybody should have the same opportunity, or you shouldn't have a classifier that performs much worse on one group than another in terms of error rate. This is called separation. Because again, you've got this causal structure, but here A and Y are flipped. It says that all of the information about A is contained in the output variable. And that or conversely, the output depends both on what group they're in and what score they're in. Which implies equal error rates because, let's see, why does that apply equal error rates? I think I'd have to think about that for a minute. This is where I ended up last time. These impossibility theorems that show that you can only have some definitions of fairness at the same time and not others. Part of the reason I assigned you the homework that I did is we know that numerically it's impossible to satisfy all these criteria at the same time. But the question remains, how big is the trade-off? And in some cases it might be a very large trade-off that you have to make, and in some cases it may be only a few percent. So that's why I'm asking you to look at the ProPublica data to try to understand what the size of the trade-off is in a real-world case. And there are some scholars who argue that actually these trade-offs are not as big as they might appear, and so maybe all this argument over definitions of fairness is overblown. Having said that, we do have reason to believe that minority groups will, in general, have lower accuracy if you build a classifier. So what is the general argument for that? Yeah.
There's less data, so sample errors are more likely.
Bingo, yeah. So there's sort of two problems. One is just less trading data. Another is the minority population may actually require a different classifier than the majority population, right? They might actually be different in some way. So say you're trying to predict whether students will graduate from a college program, and whatever the minority group is in an apartment, they may have different features that predict that, right? But as this picture is trying to show, the classifier is going to fit the majority group because that's where most of the data is. So there's a bunch of techniques that computer scientists are putting together to try to deal with these issues. The simplest thing you can do is just throw more training data in for the minority group. You can also add group membership as a feature, right? If you know whether you're red or green in this example, you can change that line of discrimination between those two positions. And a good classifier algorithm should actually learn that automatically. Again, that can be controversial as well. It depends how you feel about the idea of using group membership, so let's say race or gender, explicitly as a feature in your classifier. But it's one of the ways to solve this problem. And I suppose the only really general thing you can say is that you should probably be checking if this is the sort of thing you care about, right? So you get the classic examples of, facial recognition doesn't work as well on black women. Well, maybe you should be evaluating the accuracy on black women as opposed to just that single accuracy for the entire training set. Okay, so that sort of concludes the theoretical work we're going to do on this problem of classification and bias. The final part of this is, in some ways, the most important part. We're going to zoom out and look at the entire system around the algorithm, right? So we've been very focused on the algorithmics of this stuff because I feel like it's really important for you to get a solid introduction to what's now called FAT-ML, fairness, accountability, and transparency in machine learning. But if you're actually going to use this stuff, it's always embedded in a system. So let's talk about that. So I'm going to draw a little box. We're going to talk about the sort of risk score case again. Right, so we're going to call this, we'll just call it the classifier. And it takes in inputs about the individual case, and it takes in inputs about the training data, right? So let's say this is training data, and this is individual data, and it produces a risk score. Great. So this is sort of where we've been looking so far. Now we're going to talk about everything else. So when you actually use this, it's embedded in this much larger context. So let's draw out the whole picture here. So if you're using algorithmic risk scores to try to decide who gets bail if, in a pretrial sense, of course they're also used in post-trial, who gets parole, right? What else do you have in this system? Yeah. Yeah, okay, so the data comes from somewhere. So how do we represent that in this picture? Where does it come from? What did they train what did Compass train the classifier on?
Historical, like what happened before, like who got parole, who got...
Yeah, in this case arrest data, right? So the arrest data comes from the police department. So let's see if I can draw a police badge here. What's that? It's what?
Press the out, right? The top part.
Oh, right, I'm drawing too high. Yeah, thank you. Okay. So how about over here? Yeah. Okay. So let me draw the. I drew the badge so nice last time. Oh man. Okay. So here's the police department, right? So they produce the arrest data. In fact, I'm not going to even say training data. I'm going to say arrest data. And how do they produce it? Where does it come from? Right, do they make it up? Like what? How does this work? It sounds like a trick question, but it's not. I'm asking you to think about the entire process that generates this data. They make an arrest. Okay, right. So somewhere in here, we get the actual arrests. So an arrest is an interaction between a police officer and a defendant who, let's draw them in handcuffs here. There you go. Sometimes I can spell. So that, that depends where the, that depends on the behavior of both of these people. It depends on where the police officers are assigned to patrol. It depends on the priorities of the police department in terms of what sorts of crimes they are interested in. There's no guarantee that that's unbiased, and we're about to look at biased in arrests data, for example. And we can also have a feedback loop here where if there is some algorithm that is deciding where to send the police, you can send the police where people have previously been arrested. Right? You only get an arrest if you have the police there. So if you continually send the police where the previous arrests are, you may not actually be capturing crime rates so much as police patrolling patterns in your arrest data, right? So we can get this feedback loop where this information feeds back into the data generating system. We'll talk about these types of feedback loops in certain cases, or the potential for them. Okay, so then on the other side, what happens to the risk score? Yeah, okay. So the judge sees it in the pretrial case, right? So this goes to the judge who, let's see, can I make a robed and wigged figure here? A necklace? Yeah? What's a judge necklace look like?
Like Ruth Bader Ginsburg.
Oh, right, okay. All right, so yeah. All right, so there we go. And they've got robes as well. Okay, so there's the judge. Judge of indeterminate gender. All right, so the judge looks at this and makes some sort of determination. Or, in the more general cases, right? So in some of the cases we're going to look at, it could be someone looks at, it could be someone who decides whether someone gets a loan, or whether they're hired, or whether to do an investigation into potential child abuse, which we'll look at in a little bit. One critique of the idea of using these algorithms in the system is that maybe whoever uses the output will blindly follow the algorithm, right? Maybe they will give up any sort of case-by-case decision-making, which is kind of what we hope, it's kind of how we hope the justice system works, right? If it's your case, you want your case to be considered individually, not mechanically or as part of a group. But of course, if you're building any sort of predictor, prediction is impossible without considering other people like you, right? That's what prediction is looking at history and saying, you're similar to history in this way. So that's a more generalized argument against prediction. And maybe your case has some special circumstances, and maybe we give up our human decision-making ability by looking at the algorithm. Or maybe the output from the classifier is perfectly fair by whatever metric or metrics we use, and the judge ignores it selectively. There is actually evidence that this is happening. We'll look at a few cases, and I actually suspect this is the common case, is that people ignore the algorithmic output more or less and make biased decisions anyways. And then ultimately you get some final decision, right? We're probably missing many, many parts of this diagram. We haven't drawn the legal system, the entire institutional framework around the judge, right? So we could draw this other box here, and we'll call this the courts, right? The judge has certain incentives. Maybe there's political pressure to lock more people up. Maybe the incentive is for them to either follow or ignore the algorithmic risk score. The overall point that I'm trying to make is that the classifier is one part of a larger system, and normally the sort of $10 word that people use to describe this, it is a socio-technical system. You've probably heard this. And fairness, whatever fairness might mean, is going to be a property of the system, not the algorithm. All right? Before we move on, can anyone think of other parts of this system that are missing? I can think of at least a few more. Any thoughts? What else is missing in this picture? Yeah.
The legislative body determines what is illegal, and also maybe like how courts are regulated.
Yeah, so so eventually you expand outwards and you include the whole government, sure. Yeah, why not? Another important thing we're missing is the creator of the software, right? So that is, and this is an area of concern, that is a private company which normally is keeping trade secrets, right? That algorithm is not public. The Compass algorithm is still not public. We know a lot about it because of the extensive reverse engineering, but they've never actually said how it's built, right? Now, there's, as you'll see in your homework, it can't actually be that fancy, right? It's probably not more than a logistic regression, or it's nothing groundbreaking, because you can get the same predictive accuracy with just a few features in a logistic regression. So it's not really that exciting. But nonetheless, it is secret, and it's secret in the case of lending decisions. FICO scores are secret. For example, the FICO score algorithm is secret. It's secret in the case of hiring because you don't know what the company is using. DNA testing or DNA matching, does the DNA evidence show they were at the scene of the crime? There's a project right now to try to obtain that code and audit it in New York City. There's a talk about that next week, actually. So we can include, let's see here. I'm going to try to draw a, algco building, right? There's the front door. And they created this algorithm. And they have certain incentives as well, right? Ultimately, they have to make an algorithm that they can sell. So that depends on, somewhere in here, there's a person who chose that algorithm, decided that they were going to buy it. How do you convince them to buy an algorithm without revealing what the algorithm is? This just sort of goes on and on and on. And again, the property of fairness is emergent from the entire system. Okay? So while it's very important to understand how this box works, and we've spent, 2 classes on this? That is not the whole story. That is the beginning. The complete analysis has to ask how all of this fits together in this much larger system. Okay, so what we are going to do next is expand on that by looking at a bunch of important factors here. So the first one is data quality. This is one of the main critiques of use of algorithmic techniques in criminal justice cases. Well, the data is biased. So every one of these things we're going to talk about is the subject of intense research and debate. I'm just going to try to point you in the direction of what's going on. For certain types of crimes, we have very good evidence that arrest rates are biased tremendously. So for example, arrests for marijuana possession, the rates of usage among black and white people have been nearly equal for a long time. The arrest rates are just not, right? They're way off. So if you build your predictor based on whether someone is going to be arrested for marijuana, it's going to be heavily skewed to think that black defendants are more likely to be arrested, which is true. They are more likely to be arrested. But to the extent that we want our predictor to predict crimes and not arrests, we have a serious problem with using this type of data. So this is another one of these annoying real-world problems, which is that we often can't get the data we want. The data we want is crimes. The data we have is arrests, so we often have to use a proxy, which may or may not be accurate. So this type of data is sometimes used by critics of algorithmic methods to just dismiss them entirely. It's, the data is biased, we can't use this, it makes no sense. The best evidence I can find suggests, hang on, before we go into that. So why is the arrest rate higher in neighborhoods with more minority population? This was the New York Times trying to tackle a similar issue, which is why you have more calls to 311, right, and 911. And the police explanation, the NYPD's explanation for this, is that there's just more people who report. And there's various theories about why this might be true. So, for example, maybe you don't trust your landlord to do anything in these neighborhoods because you have crappy landlords, and so maybe you call the city instead. And what this story was the Times trying to test the police department's explanation. And so it ends up being this exercise in GIS, right? So you have to align the police precincts and the Census Bureau because you have the demographic data at census block level, you have the police data at precinct level, so you have to mess around with this in QGIS, and it's a little bit of a pain. I actually have a blog post about how to do this. And sure enough, the minority neighborhoods have more calls about marijuana. But what they found is that when you control for the rate of calls, you have higher arrest rates in majority black neighborhoods, right? So this gets into this issue of controlling for variables, right? This is always an issue when you're trying to do these types of bias stories, is that you're trying to make comparisons between different populations or different neighborhoods, and all kinds of things are changing at the same time. You really, you would really like to make statements, if you're going to talk about fairness, about, everything is the same except the race of the person. And that in fact comes out in our definitions of fairness, right? So all of this stuff that we were looking at earlier. If you look at, for example, the counterfactual fairness definition, right? You're saying, well, what would be the decision? The decision would be the same if the race was different, right? Well, implicitly what that's saying is everything else is the same. You very rarely have everything else the same. And you can kind of parse these definitions, and there's always an implicit everything else being equal, what we would call in economics the ceteris paribus assumption. But we do not have that in reality because, race determines a lot of things in American life. And so you have to do some sort of control maneuver. And so that's what they're doing here, right? They're saying, okay, well, if we look at the neighborhoods where there's the same number of calls, what we find is that we still have a greater arrest rate. So there's some translation of calls to the police into arrests, and that process that turns one into the other varies based on the demographics of the neighborhood. And the cops' explanation is that there's more crime in these neighborhoods, and so there's more police. And unfortunately, the Times didn't publish their analysis, or I don't have their notebooks, so I don't know how they controlled, and I feel like this story is incomplete, right? I feel like if you're really going to go into this and use the data and try to answer these questions, then you got to publish the data, because otherwise it's just too hard to know what they controlled for and what they didn't, and so forth. But you can see by sort of looking at this, sketching out this analysis, that this is going to be a hard thing to do, right? This is not as simple as just being like, there's more arrests in black neighborhoods. It's like, well, okay, but what else is going on that differs? There's lots of things varying at the same time.
It's interesting that it seems incomplete to me as well, because like the lead of the sentence in the next paragraph should be an explanation of whether that claim is true, if they indeed have the data.
Yeah, I mean,
it seems very sloppy even for New York Times.
Yeah, I think what happened is they sort of got about as far as they could get with what they had. And that's okay, right?
Such an easy explanation and it went unchallenged, an explanation from the police without any sort of...
Yeah, I agree. It's bothersome. It is a fact of journalism that sometimes you just have to publish, right? You're not going to have all the answers to all the questions before you can run the story, especially when the issues are very complex as they are here. So, but they could have run a follow-up. They could have published the data in code.
I also didn't read the story, but it's missing like they have their assertion. They have the police force response.
Mm-hmm.
Where's the community response in that?
Yep. Yeah, I don't think there's any discussion of, community advocacy organizations or,
Yeah, what did they say about police saying that higher marijuana arrest rates are attributable to violent crime rates being higher?
Right, yeah. And then you would get, right, but I don't know, I mean, that's useful, but then you get in sort of a he said, she said thing, right? And you can't really unravel this story without going down the rabbit hole of, the whole system, right? Like that's always the problem here. We're trying to understand systems.
But that's the job of the journalist.
Yeah.
It's messy.
Yeah, you can talk to experts. You know, I guarantee you there's people at this university who have spent the last 15 years on this question, right? So we can find them and talk to them. Final project time. Oh, and the last thing I want to point out in this is drop the police data into 4 buckets based on the percentage of your precinct's residents who are Black or Hispanic. Right? That's this controlling for idea. Right? It's very similar to adding the variable in a multivariable regression. It's the same sort of concept, but you know, there's questions of robustness. Are you going to get the same answer if you use different buckets? What about if you use buckets versus multilinear regression? You remember the Nike shoes story? How they just sort of beat that claim to death by using different methods to control. It would have been nice to see that here. And you know, it's not that I don't believe that there is a racial bias problem in policing. That happens often enough in enough places that I think it's very likely that there is a bias problem in policing. But I don't think they've really nailed it down here. Okay. So that is the case for nonviolent offenses, where we know there's severe disparities in how offenses translate into arrests. For violent crimes, the situation is probably better from the point of view of fairness. So if you read this carefully, basically what we have are 3 data sets on the racial composition of violent offenders that show more or less the same thing. And there's other, I suppose, theoretical reasons to suspect that the translation from offenses, so actual crimes committed, into arrests is going to be more consistent. For example, violent crimes tend to be more often reported. It's easier to hide smoking a joint than a body, right? So we can imagine that this translates better. Like most issues in this course, I'm not trying to make a strong argument that you should believe this. Because all of these issues are very complicated. This is the opinion of these scholars, and obviously there are other people who have looked into this issue. All I'm really trying to illustrate is that this question of whether the raw data on crime statistics is biased and in what ways is going to depend on the details, right? And it's probably even going to depend on the jurisdiction. Just because violent crimes are accurately reported in one city, or in general, these are national surveys, right? Just because on average it works nationally doesn't mean that in any particular city that's going to be the case. That's another issue in this systems view. Just because an algorithm worked in Louisville doesn't mean it's going to work in Fresno, because the judges are different, the laws are different, the data is different. It's very hard to say anything in general. We're not talking about laws of nature here. We're talking about, as the sociologists and historians say, we're talking about contingent situations, right? Every place has its own history, it developed in different ways, and I mean, you start going to different countries and it's going to be different again. So I guess the only thing that I can say in general is that there's no easy answer to this stuff. You're going to have to do it on a case-by-case basis. Then we get to the issue, sort of the outside of that diagram, which is what happens when the result is produced. So here's a very simple example. We've seen this before. I like this example because the algorithm is trivial, right? The algorithm is you add up a number of points for each previous interaction with the justice system. So, you know, each previous misdemeanor conviction, each previous felony conviction, and so forth. This point system was, again, designed to guide judges in sentencing. And the idea was that it would be colorblind, right? You're just looking at criminal history here. And so, you know, black, white, doesn't matter. If they had a felony conviction for armed robbery, you get 10 points or whatever it is. Again, you have to control for the number of points when looking at sentence length. So they did that by, again, bucketing people. And again, you've got this huge disparity in sentence length, which persists across that control variable and consists across different crimes as well. Very simple example of judges ignoring let's just go ahead and call it an objective measure and doing their own thing. Risk scores are even more complicated. They're a little more abstract. They're a little more opaque, right? At least we know the algorithm that generated this. When you have something like you know, a random forest where you can't really explain why any particular person got a particular score, it's probably even easier to dismiss. Here's another example of scores being used in practice. So you've probably heard about Chicago's predictive policing push, and there's different pieces of that. This is a piece which is called the SSL, the Strategic Subjects List, I think it stands for. We'll see it more in a second. The idea here is that you can predict who's going to be involved in a crime and then intervene beforehand to reduce crime rates, right? That's the theory. Here's the model. This is a really nice report, by the way, this RAND report. The big drawback is it's only really studied sort of phase 1 of this project, and as always, things have moved on. But it's a really good case study in how you think about these things. Interestingly, they predict not only whether somebody will be involved in a crime, but whether the victim of a crime. And they actually, the output variable is both combined, which I find actually kind of disturbing, right? The prediction is, will you shoot someone or will you get shot, right? It's the same variable, which seems suspicious to me. But I suppose if you wanted to argue for that, you'd say, well, it tends to be the same people who are involved in these types of things. I don't know, man. Anyway, here's the idea, is that you intervene before these bad things can happen. And so here's the evaluation of whether it worked. And so they looked at you know, whether this reduced the homicide rate. Basically with regression, they use something called a vector autoregression, which is, you use it for time series. You try to predict the next value in the sequence from the previous values in several sequences. So for example, you try to predict next month's homicides from all of the history of homicides up to this point, plus the history of other types of crime, on the assumption that there might be some correlation between different types of crime. That's one of the methods they used. Anyway, so you can do these types of regressions and look at the coefficients, and that helps you detrend this stuff, because obviously there's a seasonal spike here, right? There's always more crime in summer. And here's what you get. You don't, being placed on this high-risk list does not reduce the likelihood of being a victim or being arrested for murder, but it does make you much more likely to be arrested for a shooting. So what's going on there? What can we guess about how this algorithmically generated list of high-risk people is being used in practice?
Does it mean that the algorithm says, okay, so this person could be suspicious in terms of like having shot someone but not necessarily killed someone?
It's sort of the other way around. What they think is happening, and so the researchers did all this data analysis, but also a lot of like sitting in on police department meetings and interviews. It's a really nice example of combined quantitative, qualitative research. It's one of the reasons I recommend you read this paper. And what they think is going on is basically the cops are ignoring the output of this predictor, except when someone is shot, they use this list as kind of the usual suspects list, right?
And as we all know, finding leads and finding sources is the most, or one of the most difficult parts of a story. So, like if you're a police department saying, well, you have community and political pressure to find suspects and make arrests for a shooting, and you have a list sitting here that facilitates that process, makes it easier, then
Yeah.
go with that.
So it's not really being used. The idea was that you intervene before there's a crime, right? But it's not really being used that way. It's being used to arrest people after there's been a shooting, although not a murder. So I think we're talking about arrests for non-fatal shootings. And in terms of algorithmic accountability journalism, this was Chicago Magazine who FOIA'd the list and a bunch of information, basically a bunch of features for each person on the list, and tried to figure out what gets you on the list. Now, this is not really what gets you on the list. You kind of want this to be regression coefficients, but they're not. This is the features of people on the list. So it's what are the features given that you're on the list. Regression coefficient is, it's the other conditional probability, right? What makes you get on the list given these features? Or what's the probability that you're on the list given these features? Whereas what we're looking at here is what is the probability that you have these features given that you're on the list? So they're really not the same, but maybe we can get a little bit of insight and say that, well, it picks gang members and people with drug arrests. I do think it's interesting, and I think it's important. I think it is important to do this type of journalism where so for example, this list was not publicly available. There was a little bit of a battle with the police department to get this list of names, and it was important that somebody try to figure that out. Nonetheless, they are pressing on. This strategic subjects list is only one portion of their predictive policing system. So they've got this whole system of sort of decision-making centers. And they do a lot of predictive policing stuff, right? So the standard predictive policing thing is you use the history of crimes to try to predict where new ones are going to be, and you send officers there. And this is the most direct illustration of a place where there can be a feedback loop, because again, you have arrest history, not crime history. And so if you send the officers to the places where they've previously made arrests, well, by gosh, you're going to have more arrests in those places where there's officers, right? You don't get any arrests where there are no police. So you got to be careful about that stuff, and that's one of the major criticisms. But then again, if for violent crimes in particular, if you believe that most offenses, the offenses translate into arrests in a much more balanced way than for misdemeanors, then maybe it still makes sense. In any case, they're investing in this further. Now I will give you my opinion a little bit, and sort of the whole algorithmic risk score, criminal justice thing. One of the criticisms that has been expressed in the sort of research literature and by the organizations which are concerned about the use of risk scores and other types of technology in criminal justice is that the risk scores will be blindly followed by the judges, and it will eliminate human decision making, right? We're just going to give up our autonomy, our individual consideration of individual cases. in the Florida case, which you've seen, in, I believe it was Kentucky where risk scores came in, and in terms of another study, which we'll see in a second, of decisions by New York State judges as compared to a very simple classifier. By and large, I mean, it's still early, but every case I know of where we looked at what human judges did with risk scores, they kind of ignored them. By and large, it is not the case that humans are slavishly following the algorithmic results. Seems to be more common that they ignore them and do their standard thing anyway. In other words, if you are concerned about the fairness of the overall system, my general sense, or if you like, my prior, would be that what we need is people following the algorithmic results more closely, not less closely. This is a hard thing to nail down, but that's where I see the weight of the evidence. There's no doubt some incredible reporting to be done on this topic. Okay, so we've been talking about criminal justice a lot. Criminal justice is, it's been very well covered. It's very consequential. It's very controversial. It's a rabbit hole. You can really, really go down this hole. And what I will recommend to you, if you have an interest in this stuff, is a recent piece by Stephanie Weikstra at Vox. We've studied the algorithmic portion of this, and this will be linked from the syllabus, extensively. But this whole issue of risk scores in pretrial sentencing is really come to the forefront as one component of bail reform. And if you want to understand not just the algorithm, but that whole thing, this is as good a primer as you are going to get. This is the a massive amount of context to how these risk scores are used. And she mentions risk scores in here, right? Risk assessment. So, she's got one section on risk assessment, which is really good and has lots of links. So,
Is Vox based in New York?
Vox is in DC.
Vox is in DC.
Yeah, but she's a freelancer. You can work from anywhere. In particular, that it has some interesting links to evidence for this idea that I just mentioned, that basically judges' decisions are a lot more biased than the algorithmic decisions. But to really get into this, it's a very complicated issue, and I haven't really even touched on the legal points about this. But if you want to, there's so much good reporting to be done on this, and this would be a great place to start. I want to talk about two other domains where algorithms with social impact are widely used. You may have heard of a new type of lending, which rather than basing it on traditional FICO scores and so forth, there's this whole traditional process for how banks decide. There are these startups which say, we don't care about FICO scores. We're just going to collect all of this other types of data. And we think we can make much more accurate predictions about who's going to default. And part of the way this is pitched is that this is going to extend access to credit. So as it says here, one of the problems that people have getting access to credit is they don't have a credit history. And there are groups which might be perfectly credit worthy but don't have any way to prove that, such as recent graduates and immigrants, right? So you come from another country, you have no American credit history, you can't get a mortgage to buy a house or a car or student loans or whatever it is you want, right? So they make this social argument about why they should be allowed to use all of this personal information to decide who gets a loan. Of course, it's our job to evaluate these types of arguments and see if there's anything behind them, right? Does this make sense? This paper, the references at the bottom, is a very interesting paper. It looks at the effect of introducing better prediction for defaults on the American mortgage market, so housing loans, which is, of course, heavily regulated, and there's a long history of unfair discrimination against people of color. You may have heard the term redlining. This is where banks used to literally draw a red line on the map and say, okay, we don't give mortgages in these neighborhoods, right? And it's a beautiful analysis in part because it's done by two people in one of the federal banks. And so they have access to this huge data set of loans. So they have the underlying data about who gets loans and who doesn't and what their demographics are. And so they can analyze what would be the effect of better prediction retrospectively because they know historically who paid off their mortgages and so forth. And the point that they make here is, I think, a really good framing for this type of reporting, which is that if you have better prediction of outcomes, there's always going to be some winners and losers. The winners are going to be those people who should have gotten a loan but didn't. The losers are going to be those people who were going to default, but there was no way to know that, and so they got a loan anyway. Now, it's not entirely clear whether giving somebody a loan if you know that they're going to be unable to pay it back is a good thing. That is another very complicated argument. Debt is a very complicated question, and there's lots of good reporting. ProPublica has a whole series on debt, which I recommend you read. But we can say that this general frame will hold for any predictive technology. As you get better predictions, some people are going to win and some people are going to lose. And that's a way into a story, right? You can always use that frame to start your reporting. I mean, this is a classic journalism frame, right? The new law is passed. Who are the winners and losers, right? This is basic important stuff. And in terms of fairness or distributional characteristics, what they say is that they do think that better prediction through machine learning in the mortgage market is going to give more people access to credit. So that's good, right? And as they say, marginally reduces disparity in acceptance rates across race and ethnic groups. However, they find that, so this is a very sophisticated analysis. It looks at not only who gets a loan, but at what interest rate. And under their model, what happens is that Black and Hispanic borrowers have a much wider spread of rates. So the disparities come about not so much because some people get mortgages and some don't, but more that some people are going to see their rates go way up because the machine learning model predicts that they're much riskier, and some people see their rates go down. So the disparity actually ends up being within group in their models here, which is a type of disparity we don't normally talk about. I've also got a notebook that's linked from my lead course, and I can add that to our links, which analyzes data from Lending Club, which is one of these new style algorithmic lending organizations. They actually publish their complete loan portfolio as this huge data set with 10 million rows. And so I used that to do a very simple, including the history of the loan, right? So I used that to do a very simple analysis that asks the question with improved prediction. So what I do in that analysis is I compare a very simple machine learning model with a slightly more accurate machine learning model because I give it more features, and ask the question, what is the income distribution of the people who get loans under the inaccurate model and the more accurate model? Now, because of the way I set this up, I don't claim that this particular test says anything interesting, but perhaps it illustrates the methodology, right? If you can get the data, you can do this type of analysis and say, okay, does this extend credit to poorer people, for example? It's hard to get the data, but it is out there. Yeah.
I went to this talk yesterday with there's this new startup which is creating this machine learning algorithm to fight financial crime.
Mm-hmm.
So they're creating software that they sell to banks commercially so that they can stop money laundering and stuff.
Oh, nice.
And they talked about obviously like how they're being so efficient and they have 10 observables that they collect that the neural network learns and is much, much smarter than any rule-based system.
Mm-hmm.
I was very interested to be like, okay, what is the data that I can get? Whatever I spoke to them, they were like, oh, this is the only system. Somebody asked about the fairness of the system, like, would it discriminate against people who've, like, obviously either like by race or some sort of other differentiation? And he was like, this is the first system that's ever been used. We don't know what the implications are.
Right.
So what would you say like would be the first way to go get data on it?
Well, you'd have to talk to them, right? And see if they're willing to share the data, or whether they've got someone who's studying the ethical implications of this technology already. Right, and remember, ethics are not, these distributional issues are not the only lens, right? Because the people doing this are doing it because they genuinely believe that there's a net social benefit. So you can ask questions like, so is there really a benefit, right? As compared to, what are we doing now? And what are the ways this is better? And what are the ways this is worse, right? So with any change, you can always do this winners and losers frame. And the winners and losers may be distributed across race or gender. They may be distributed across income. They may be distributed across countries. This really penalizes foreigners, right? There could be all sorts of, this is really hard on the coal industry, like whatever, right? There's all kinds of ways that the benefits could be unequally distributed.
It was really interesting, especially because he was like, we discovered the Panama Papers 6 months before the story, and I was like, and what did you do with it?
Yeah,
We
right.
sold it.
We sold it?
Like we gave it to a bank.
Uh-huh.
And I don't know what the client did with it.
Yeah, well, the way that society regulates this stuff, it's a really interesting question. So, law enforcement is fascinated by money laundering, right? That's their job.
Mm-hmm.
As you've seen, journalism also does a lot of money laundering investigation these days. The accounts of the world don't add up. Huge amounts of public money are being diverted away from people who need it. The amount of stolen money flowing out of Africa is greater than the amount of foreign aid flowing into it, right? So if we could solve the problem of diverted funds, that would more than double the aid budgets. So it's a big issue, and journalism and law enforcement are in some sense working on the same problem. And they have different advantages and disadvantages. So law enforcement can subpoena information. They can use legal powers to compel the production of data, which we can't. On the other hand, we get to work in public, right? And as the saying goes, the crime is that it's legal. So law enforcement can only get involved when there is a potential crime. Journalism can get involved when something bad is happening that's not even illegal. So there's various advantages and different advantages, and one of the really interesting questions is how these various mechanisms interlock and relate to each other. Also, journalism is not capable of punishing anybody, which means people can often talk more freely to journalists, right? If you can guarantee anonymity and for somebody, then maybe they will tell you about all of these crimes that they may be implicated in, right? Whereas they would not talk to law enforcement because their lawyer would advise them not to incriminate themselves. So, a very complicated relationship between the two. This is a really interesting case. This is another one which has been heavily covered, and the syllabus includes 2 links. One is to a paper by the people who built this system, and one is Virginia Eubanks, who wrote Automating Inequality, covers this case in great detail. The conversation that they're having is fascinating to me. They're sort of talking past each other, so I urge you to read both the paper and one of Eubanks' articles carefully and try to read them against each other. So this is from this paper that just came out a month ago on how the system works and what they're doing with it. And we talked about feedback loops very briefly. I find this fascinating. They were worried that so here's what the tool is meant to do. Someone calls this child abuse reporting hotline, and after this call, the person who took the call has to make a choice. Do you screen this call out, or screen it in, meaning start an investigation and follow up? So let me show you what this looks like. Oh, everything's so small. Oh, this is paper we'll talk about later today. So this is a flowchart of the process. And this is really a wonderful paper. This is really state of the art in the algorithmic fairness discussion. But anyway, here's a little bit of this context. Oh, interesting. Apparently I can't zoom it bigger. So here's how this goes. So you get this this call, and really? I can't zoom this? That's annoying. Okay. You get this call, and we've always had this step where the screener, the human, assigns risk and safety ratings, which are sort of these this risk score. And then now the algorithm weighs in, and then eventually they have to say, okay, we're not going to follow up, or we are going to follow up, and after the investigation, either there's some sort of intervention or there's no intervention. So the purpose of the algorithm is to help the screeners decide which branch to take here, right? Do we do an investigation or not? And the thing it's designed to do is help the screeners integrate all of the previous case history for this child, right? So were there previous calls? Were there previous calls for the siblings, right? Because that's a risk indicator as well if you've had a report for someone else in that family or someone else in that household. Notably, the algorithm does not take into account the content of the current call because the algorithm runs before the contents of the current call are entered. So it's just trying to summarize the history. And what they're worried about is that if the people working in the Child Protection Services Agency use this risk score to so the model is trained on who gets placed in foster care within 2 years, right? That's the endpoint that they use. But if the risk score influences the decision to investigate and ultimately has influence on the decision about whether someone is placed in foster care, then you get the same feedback loop you get with sending the cops out to the places where you've made the arrests before. Right? So there is the possibility of this feedback loop. And to try to ameliorate that, part of the design of the system is that they train it on an outcome that the people who use the algorithm don't have much influence over. So in particular, oops. Where did I go? Okay. The decision to place a child in foster care is made by a different group of people than the people screening the calls. And I mean, that doesn't necessarily break the feedback loop, but it certainly is an attempt to weaken it a little bit. So the issue here is, as they're saying, workers affect the outcome predicted by the model, e.g. substantiate cases that the model tells them they likely should. Then we get to this type of ROC analysis. This is like the classic fairness metric stuff that we were looking at. And so we have race-specific ROC curves. And the way they assign the risk scores is by percentiles, which means that you actually get a different threshold for different races because it just looks at, Are they within the top 5 riskiest, the top 10% most riskiest, the top 15%? So you actually get very different risk scores for different races. This is sort of their old algorithm. This is their new algorithm. The old algorithm was a logistic regression, which they originally chose because they wanted it to be explainable. But they found that nobody was really cared about the explanations anyways of why the algorithm produced a score, and that a random forest had much better predictions. So they've switched to a random forest. And so you can see the false positive rate actually differs in the old case substantially between race and a little less now. And it's just the case that they have better prediction for certain groups. So for example, I have no idea why, but for the unknown race, right, where they don't know the race, the AUC is much higher. I'm really not sure what's going on there, and that seems like it's probably an interesting artifact. And part of the reason they want to do this is because there's already bias in the system. So we know for a long time black children are disproportionately more likely to be placed in foster care. And there's a bunch of different reasons, right? There's a bunch of different stages in this pipeline where this could be happening. They know that introducing this tool, remember, it's this whole contextual problem, only changes some of these issues. But if they can build a classifier which has this sort of fairness property of, let's say, calibration, so that the same score means the same thing regardless of race, and those scores are used in the same way to decide whether to screen in a call, that is to do an investigation, that has the potential to reduce bias at certain stages of this pipeline, although not others, of course. Unfortunately, and this is another data point in the people ignore the risk scores, they analyze this a bunch of different ways. This is probably the most informative graph. So the x-axis here is the risk score, and so because this is a calibrated algorithm, you can imagine that the actual risk of being placed in foster care is increasing monotonically with risk score. But the decision to screen in, which is this purple, so the decision to follow up investigation, does not increase very quickly with this risk score. If the decision to screen in was based only on the probability that someone is going to end up in foster care, this would be a much steeper curve. In particular, and this I find fascinating, the highest 3 scores are a mandatory screen-in, right? So this should actually, we should actually not have any green for these last 3 bars if people were following the procedures which theoretically they're required to follow, which means a manager is overriding the algorithm or overriding the policy, I should say, in about 25% of cases. So basically they built this tool, they calibrated it for all of these fairness properties, and then they deploy it into production, and the workers kind of ignore it. So we're not really going to get fairer outcomes as a result of this deployment. Now, the broader criticism, and this is what I read as Eubank's criticism, is that it doesn't matter if you make a better screening tool, because ultimately the problem is that we are not funding child protective services. Right? These people are very poorly paid. We don't have the volume of foster homes we need. And changing the accuracy with which we can deploy resources is not going to solve the problem of having far too few resources. So in that sense, talking about better screening algorithms is talking about the wrong thing. and is a distraction from the broader problem of why are we not adequately providing the resources for these children to thrive. So that's a different type of criticism, which is outside the algorithmic frame and outside even the systemic frame, right? She's just saying, none of this matters if it's not funded. Okay, so thoughts on all of this?
Is there a story that we could do of like, imagine there's a hypothetical situation of like unlimited funding, then how would these algorithms work?
Sure, right? If we funded them to the levels that they need, then would this help?
Yeah, if you didn't have to cut corners.
I think you would have to look very carefully at how people end up using these scores, right? If these things are really more accurate and more predictive than the human decisions. And by the way, another one of the charts in this paper shows that there's very low correlation between the human assigned risk scores and the algorithmically assigned risk scores. And because we know that the algorithmic risk scores are extracting about as much data or much information as possible from the data that's available, that means the human scores are actually not very good, right? They're not good predictors. So the scope for improvement is probably really big. If these scores could be used and integrated into the system in the right way.
I'm wondering, is there a way to examine exactly which cases were overridden?
Sure, and that's going to be their next paper. They say at the end that they're investigating why people are overriding them, right? And maybe there's a good reason.
Part of me wonders if it's just like, we don't understand what it's doing, we don't want to trust it.
Yeah, people might not trust the scores. They might not. They might consider that it's taking away their autonomy. There's all sorts of things that could be going on here.
Could be a discussion of low wages, turnover rates.
Yep.
And the material conditions of social workers would be useful.
Yeah. I'm still waiting for. I think there's a great story to be done here for someone who wants to get deep into this. We've seen the stories which are like, these risk scores are going to be biased, they're just not going to solve the problem. I think in this cultural moment, because of the ProPublica discussion and the FAT-ML community and sort of where we've been, the general perception is that these algorithmic methods are biased. I think the reality is a lot more complicated, and we haven't seen an in-depth, smart, and balanced article. Because, of course, the people doing this, right, why are we bothering at all with all of this technology? And the reason is, there is reason to believe that this stuff could help, right? So what are the reasons to believe that it could help? What are the reasons to believe that it's going to make things worse? What's actually happening on the ground? Where do we go from here? That article hasn't been done yet.
It's also interesting, like comparing predictive policing to predictive child welfare. They're very different because money is being poured into local police departments, and money for policing is growing by a huge amount, whereas the welfare state is being constrained, and so these tools in child welfare are a response to constrained budgets, and trying to do more with less personnel.
Yep.
What exactly is this scoring tool? Where, it says that it's presented at a specific juncture.
Mm-hmm.
So what is the input at that point? Is there a way that, eventually down the line the tool could replace the humans, and that's a way to cut costs?
Could this tool replace humans? I don't think so, right? Somebody still has to answer the phone. Right? I don't think anybody is talking about replacing humans. This is meant to be a decision support system, so to help humans make better decisions. When they're very pressed for time and they may not be able to read the complete case history. So that's one issue, is they're just not going to be able to assimilate all of the data that's available. The other is that humans are just not that great at making predictions. We've got 60 or 70 years of evidence that people are inconsistent in general. Now, of course, they may be all right in a particular domain, but my bias would be that they're lacking any other information. We should assume they're not that great, and that's what they found here as well. That's the end of that deck. But this gets to the question of why do people want to implement these algorithms, right? And you can be really cynical and say, oh, because there's money to be made. It's like, okay, well, that doesn't explain, there's not that much money to be made doing this stuff, right? That doesn't explain why all of these researchers are doubling down on this stuff. This is produced by a bunch of academics. And, even the algorithm's critics admit that it was done they did everything right in terms of consulting with the community and, holding meetings with various stakeholders before they started and hiring people to do an independent ethics review of the system. So this paper is very interesting because it's a case study of sort of everything going right and yet the outcome still being not that great. Okay, your homework, which I will assign you shortly, is you're going to take the ProPublica data, so this should be familiar. You're going to build your own classifier, which is a logistic regression. So we don't have the COMPASS data, like the 137 questions. We're basically just going to use age, criminal history, a few other things. This is actually, in the notebook we used last class, this is actually in there. So basically, for this, you can just cut and paste that code. And you will find that it gets about 65% accuracy, and it's almost as good as the actual North Point algorithm. So you're going to build that, and then now that we have our own classifier, we can mess around with it. So you're going to write this function which applies a different threshold to each group, and you're going to tell me, and you're going to set the threshold so that the false positive rate is equal between black and white defendants, and then you're going to tell me what that does to the other confusion matrix metrics. So we're going to look at a real-world example of trying to modify a classifier to make it fair by one of these definitions. And optional, if you like, I just put this in here because it's interesting, you can do a little more analysis here and figure out how much information about race is actually leaking through into the classifier. Remember we talked last time that it's almost impossible to hide race and gender from in the data. Well, now you're going to find out how well you can guess race just from the features that the classifier is using.